I welcome all to another lecture on power quality problems and solutions. In previous lecture, we discussed a three-phase sinusoidal balanced system, and we derived the mathematical expressions for instantaneous power delivered by three-phase source to three-phase load. The source was star connected, load was also star connected, and we had a neutral connection also there. We also derived the mathematical expression for instantaneous reactive power using H. Akagi's theory, which was based on ABC to alpha beta O transformation, coordinate transformation. In this lecture, I am going to discuss instantaneous active and reactive powers in three-phase system. We are going to take different types of three-phase systems. Let me first of all write here instantaneous active and reactive powers in three-phase AC systems. Now the question is, what type of three-phase AC systems are we going to discuss? We are going to discuss and derive the mathematical expressions for instantaneous active power and instantaneous reactive power for various three-phase systems, like first of all three-phase balanced system. We have already derived the expression for a three-phase balanced system in the previous lecture. I mean the mathematical expression for three-phase active power and three-phase reactive power. We are going to discuss it today also. It may be a sort of repetition of what we have already learned, but we are going to use a different approach, the approach of phasor diagrams. This will be followed by three-phase unbalanced system. Three-phase unbalanced system. In three-phase unbalanced system also, we will try to derive the mathematical expressions for instantaneous power, that's instantaneous active and instantaneous reactive power, and we are going to compare the two systems, three-phase balanced system and three-phase unbalanced system. Some very interesting results will be available when you analyze a three-phase unbalanced system, and you will see what are the drawbacks of three-phase unbalanced system. The mathematical equations that we will derive, they will tell you everything about a three-phase unbalanced system. That is how a three-phase unbalanced system creates problems in the system, increases the losses and all that. Third system that we are going to discuss is three-phase balanced system. Three-phase balanced system with harmonics. I mean, your first case is three-phase balanced system, but it is without harmonics. And then we will discuss three-phase balanced system with harmonics. And last is three-phase unbalanced system with harmonics. Three-phase unbalanced system with harmonics. You see the first two cases that we are going to discuss, three-phase balanced system and three-phase unbalanced system. In both the cases, the system is unbalanced, either balanced or unbalanced, but there are no harmonics injected in the supply voltage. The source voltage is without any harmonics. But in the third case, C, and in the fourth case, we'll discuss three-phase balanced system with harmonics and three-phase unbalanced system with harmonics. So these will be, there will be a sort of marathon type discussion on all these types of systems. And believe me, there's a lot to learn, new things that we are going to learn while analyzing all these systems, which I am sure you have not studied in your BTech curriculum, BTech course. At the most, you might have studied a three-phase balanced system in your BTech course. But three-phase unbalanced system, then three-phase balanced system with harmonics, and three-phase unbalanced system with harmonics we are going to study in this course. The question is, why are we going to study three-phase unbalanced system or balanced system with harmonics and unbalanced system with harmonics? Because these are all power quality problems. And we are going to analyze mathematically and theoretically also these systems which are, balanced with harmonics or unbalanced with harmonics or simply unbalanced without harmonics. And the idea is to analyze them mathematically, to study them, to understand, so that we can design a proper compensation system. I mean, this is the groundwork that we are doing for designing the compensation system. You have to design a compensation system for, compensating the unbalance in the three-phase system, for compensating harmonics, and in this system for compensating unbalance as well as harmonics. But my question is, how can you design a compensation system without understanding the behavior of system when these types of power quality problems are there? So that's why this is a sort of groundwork. Whatever we are studying these days for last few lectures is very, very important. We will derive some very important mathematical expressions, some very important conclusions will be there, and based on that mathematical analysis, we'll be able to design a better compensation system for addressing these power quality problems. Let me start with first type of system, that is three-phase balanced system. Three-phase balanced system. Now, obviously, it does not have any harmonics. It is a three-phase balanced system without harmonics. Okay. Now, let us define three-phase voltages, instantaneous voltages, VAT, which is equal to root 2V sine omega t. Phase B voltage will be VBT equal to root 2V sine of omega t minus 120 degrees, and VCT will be equal to root 2V sine of omega t plus 120 degrees. This is a set of three-phase balanced voltages. Balanced set of three-phase voltages, I would say. In terms of phasor, how do we write these equations? We can write VA equal to V at an angle of 0 degree, because this VA is root 2V sine omega t. There is no phase angle or phase shift as far as this phase A voltage is concerned. It is taken as reference voltage. So in terms of phasor, we can write it as VA equal to V at an angle of 0 degree. Then what about VB? Phasor VB will be equal to V at an angle of, it's at minus 120 degrees. Minus 120 degrees. And phasor C voltage, phase C voltage VC, that is this, it is at an angle of plus 120 degrees. So it is V at an angle of plus 120 degrees. Okay. So this is it. Now it will be clear to us if we draw the phasor diagram, and with the help of phasor diagram we can analyze our systems. So let us try to draw the phasor diagram. In the phasor diagram, for example, if I draw the phasor diagram, this is my phase voltage VA, which is equal to V at an angle of 0 degree. That is this phase A voltage. Phase B voltage is at an angle of, it has also same magnitude or amplitude V, but it is lagging behind phase A by 120 degrees. So it will be somewhere here. So this is my phase voltage VB, which is equal to V at an angle of minus 120 degrees. And my phase voltage VC is also having same magnitude V, but it is at an angle of plus 120 degrees with respect to VA. Okay. Minus 240 degrees with respect to VA. If you move this in this direction, or in this direction, it is at an angle of plus 120 degrees. So this is your VC. This is VC equal to V at an angle of plus 120 degrees. Okay. This VC lags behind VA this way by 120 plus 120, 240 degrees, and this way 120 degrees. That's why I have written plus 120 degrees. This way it is minus 240 degrees, and in this direction it is plus 120 degrees. Now I want to show the line voltages. Okay. Now what are my various line voltages? My various line voltages are VAB, these phasors, VBC and VCA. These are my various phasors. So now as far as this VAB line voltage is concerned, see, if this is your VB, this will be minus VB at an angle of minus 120 degrees. Minus VB or minus V. Okay. This is minus V, minus VB equal to minus V at an angle of minus 120 degrees. Because in this direction it is VB, which is equal to V at an angle of minus 120 degrees, and this is 180 degrees phase reversed voltage. And obviously it will be minus VB. It is equal to minus V at an angle of minus 120 degrees. Now this is your VA, this is your minus VB. What is VAB? VAB is the phasor sum of these. So use the parallelogram, this addition technique. So this will be your VAB. This is VAB. And what is this VAB? It is VA minus VB as per this addition. So once you know VAB, you can find line voltage VBC also. Now, if this is plus VC, what will be this? This will be minus VC. Minus VC equal to minus V at an angle of 120 degrees, because in this direction it is plus V at an angle of 120 degrees. In this direction it is minus V at an angle of plus 120 degrees. Okay, so this is VB, this is VC, so you can get VBC. Again you use this addition, this is the parallelogram, and this is your VBC phasor. VBC is VB minus VC. And similarly you can draw the phasor for VCA, which is VC minus VA. This is VC, and where is VA? If this is plus VA, in this direction it will be minus VA. Minus VA equal to minus V at an angle of 0 degrees. Again use parallelogram law of addition. So this is VCA. So I repeat again, these are our line to neutral voltages or phase voltages, VA, VB and VC. And from these phase voltages we have drawn the phasors for line voltages. Like we know VAB is VA minus VB. This is our VA. In this direction it is plus VB, in this direction it is minus VB. So VA minus VB, this vector or this phasor. Similarly, VBC is VB minus VC, and VCA is VC minus VA. Okay, so let us write the mathematical expressions for these line voltages. Now, my various line voltages are, first line voltage is VAB, which is VA at an angle of 0 degrees minus VB at an angle of, VB is at an angle of minus 120 degrees. That is equal to V at an angle of 0 degrees minus V at an angle of minus 120 degrees. That is equal to V. What does phasor angle of 0 degree mean? It means cos 0 degree plus J sine 0. Okay, minus, what does this angle of minus 120 degree mean? It means cos of minus 120 degrees plus J sine of minus 120 degrees. This is what we mean by these phasor angles. Okay, so that is equal to V times cos 0 is 1, sine 0 is 0, so I will not write this term, minus, what is cos of minus 120 degrees? Cos of minus 120 degrees is cos of plus 120 degrees, and that is minus 1 by 2. Minus into minus is plus, so this is plus 1 by 2. and then plus, this is sine of minus 120 degrees, that is minus sine 120 degrees. And what is sine 120 degrees, by the way? It is root 3 by 2. Sine 120 degrees is j root 3 by 2. Okay, so this is further equal to v times 1 plus 1 by 2 is 3 by 2 minus j root 3 by 2. Okay, fine. This further can be written as like this. So your VA line voltage VAB will be equal to V times what I can do, okay, let me write it again, 3 by 2 minus j root 3 by 2. So VAB will be equal to, if I take root 3 outside and V is also there, so here also it will become root 3 minus j 1 by 2. Root 3 because root 3 into root 3 is 3 and root 3 into 1 is root 3. So that is it. So it is therefore it is VAB, line voltage VAB is root 3 V times root 3 V times root 3 by 2 plus j, is it plus or minus? J 1 by 2. Okay. So what is that equal to? That is equal to cos 30 degrees. See, if you find cos 30 degrees, that is at an angle of 30 degrees. Angle of 30 degrees means cos 30 degrees plus j sine 30 degrees. Okay. So one mistake we have done here. It was minus sine. It was minus sine or plus sine? Yeah, it was minus sine 120 degrees. Minus and minus makes it plus. Please make a correction here. In the one of the early steps when we were finding this minus and this minus becomes plus because there was already a minus here. So it becomes plus here, plus here. So please make the corrections. So what I am telling you, this VAB will be equal to root 3V at an angle of 30 degrees. What does angle 30 degree mean? It means cos 30 degrees plus j sine 30 degrees. And cos 30 degrees is root 3 by 2, sine 30 degrees is 1 by 2. So this root 3 by 2 plus j 1 by 2 can be written at an angle of 30 degrees, a phasor angle of 30 degrees. Okay, so that is about VAB. Therefore, VAB I can write here is equal to root 3V at an angle of 30 degrees. So similarly, we can find VBC. Once you know VAB, now we can find VBC. VBC is equal to VB minus VC. And that is equal to, what is, by the way, VB? VB is V at an angle of minus 120 degrees minus VC. VC is V at an angle of 120 degrees. Okay, so that is equal to V. If I take out, it is cos minus 120 degrees plus j sine of minus 120 degrees. That is this first term minus times. What about second term? Second term is cos 120 degrees. Sorry, cos 120 degrees. This cos 120 degrees minus j sine 120 degrees. J sine 120 degrees. That is this. So that is equal to V times, what is cos 120 degrees again? Cos of minus 120 degrees is equal to cos 120 degrees, and that is equal to minus 1 by 2. We already know. And what is, this is plus minus j sine 120 degrees is root 3 by 2. So minus j root 3 by 2. Then minus cos 120 degrees is again minus 1 by 2. Okay. Minus j root 3 by 2. Because sine 120 degrees is root 3 by 2. Okay. So this is here minus cos 120 degrees. Minus to already hai, and cos 120 degrees is minus 1 by 2. That minus 1 by 2 and minus, it will become plus. So this minus 1 by 2 plus 1 by 2 goes. So this becomes equal to V times, what is minus j root 3 by 2 I mean, if you take minus out, this is root 3 by 2 plus root 3 by 2. That is root 3. So this is minus j root 3. So what I will do, I will take root 3 out. So what is inside? Minus j. That's it. So therefore VBC, I can write, therefore VBC is equal to V minus j, and that is equal to V at an angle of minus 90 degrees. Because what does j mean? J means an angle of 90 degrees. So therefore this is your VBC. और आपकी VBC कहाँ है? ये है आपकी VBC. So this is equal to V at an angle of minus 90 degrees. ये आपकी दूसरी लाइन वोल्टेज आ गई. उसके बाद VCA है, ये वोल्टेज VCA. Let us derive a relation for VCA also. Now we already know this VCA is equal to VC minus VA. So this is equal to VC minus VA. By the way, what is VC? ये आपकी VC है. VC is V at an angle of 120 degrees minus VA. VA है V at an angle of 0 degree. That is equal to V, if I take V out, so this is cos 120 degrees plus J sin 120 degrees. उसके पास माइनस है cos 0 degree minus J sin 0 degree, because this phase angle is 0. That is equal to V. Cos 120 degrees is again minus 1 by 2 plus J sin 120 degrees is root 3 by 2. And what is cos 0? It is minus 1. Sin 0 is 0, so I am not going to write that. That is equal to V times minus 1 by 2 minus 1 is minus 3 by 2 plus J root 3 by 2. So this becomes equal to, if you take root 3 also out, root 3V, so this will be minus root 3 by 2 plus J 1 by 2. Root 3 into root 3 is 3, root 3 into 1 is root 3. Okay, and what is this equal to, by the way? This is equal to root 3 V times, this is an angle of 150 degrees. What does this phase angle of 150 degree mean? It means cos 150 degrees plus J 150 degrees, J sin 150 degrees. Cos 150 degrees, if you compute, that will be minus root 3 by 2 plus J sin 150 degrees will be 1 by 2. So this is equal to a phase angle of 150 degrees. So therefore VCA line voltage is equal to root 3V at an angle of plus 150 degrees. So यह आपकी VCA है. It is V at an angle of plus 150 degrees. So all the phase voltages and all the line voltages are known to you. So therefore if you find the instantaneous power, therefore instantaneous power is given by PT, that is simply given by VA IA plus, phase quantities VB IB plus VC IC, and in terms of this coordinate transformation, it is V alpha I alpha plus V beta I beta plus V naught I naught. I am not going to repeat that. We have already derived that in previous lecture. That is 3VI cos phi. This is instantaneous power, which is equal to average power or active power, and which is a constant term equal to 3VI cos phi. Now we can derive the mathematical expression for instantaneous reactive power. So this is our instantaneous power. We already know, we have already derived it in the previous lecture. What we can do, we can derive the instantaneous reactive power expression. So I can write instantaneous reactive power is given by instantaneous reactive power from the expression using H. Akagi's theory, where we use ABC to alpha beta O transformation, coordinate transformation. And if you remember yesterday in previous lecture, we got the mathematical expression for instantaneous reactive power. What was that? That was equal to minus times, just please go through that, line voltage VBC into line current IA plus VCA IB plus VAB IC whole divided by root 3. This is the expression that we got in the previous lecture. The expression for instantaneous reactive power in a three-phase balanced system in terms of line voltages and line currents. VBCIA plus VCAIB plus VABIC divided by root 3. Of course, minus of everything. Now we have the expressions of VAB, VBC, VA. but we have the expressions in terms of phasor, like VA is equal to V at an angle of 30 degrees. VB phasor is equal to V at an angle of minus 90 degrees. And VC phasor is equal to V at an angle of 150 degrees. Just few moments back, we got it from the phasor diagram. So these are the phasor quantities. So instantaneous values of these voltages, therefore, VA, this is VAB, this is VBC, and this is VCA. VAB phasor is equal to V at an angle of 30 degrees. Phasor VBC is V at an angle of minus 90 degrees, and phasor VCA is equal to V at an angle of plus 150 degrees. We derived these expressions just few moments back from the phasor diagram. So therefore, what is the instantaneous value of this phasor voltage VAB? It is root 2, root 3. In fact, I think it is root 3 times V. This is also root 3 times V. This is also root 3 times V. Okay, root 3V 30 degrees, root 3V minus 90 degrees, root 3V 150 degrees. So this is root 3V sine of, what does 30 degree means? Omega t plus 30 degrees. This means this line voltage VAB leads the phase voltage by 30 degrees. And what is this root 3V? It is the RMS value. And if you have to find peak value, you have to multiply it by root 2. क्योंकि आपकी voltage जो होती है V equal to V max sin omega t होती है, sin of omega t minus phi. What is this? This is RMS value. अगर आपको V max निकालना हो, you have to multiply RMS value by root 2. So it is root 2 into root 3V, because root 3V is its RMS value, root 2 into root 3V sin of omega t plus 30 degrees. तो यह आपकी expression है for VAB. Similarly, what is VBC? यह आपकी VBC है, that is root 2 into root 3V sin of omega t. It is at an angle of minus 90 degrees, so minus 90 degrees. And VCA line voltage, instant expression for instantaneous line voltage VCA, that is this, is equal to root 2 into root 3V sin of omega t, and it is leading by 150 degrees, plus 150 degrees. So with these mathematical expressions for line voltages, instantaneous line voltages VAB, VBC, and VCA, we can substitute them in this equation. Let's call this equation as equation 1, and we can get the mathematical expression for this instantaneous reactive power. So therefore, from equation 1, what is instantaneous reactive power? That is equal to minus times VBC. VBC, just few moments back you have written, that is root 3 into root 2V sine of omega t minus 90 degrees into line current IA. IA is root 2I sine omega t, phase A current, plus VCA. VCA also you have written few moments back, that is root 3 into root 2V sine of omega t plus 150 degrees into IB. IB is root 2I sine of, in fact, this is sine of omega t minus phi, because current lags behind voltage by a phase angle phi. Okay, so what is IB? IB is root 2I sine of omega t minus 120 degrees minus phi, plus VAB. VAB is root 3 into root 2V sine of omega t plus 30 degrees into IC. IC is root 2I sine of omega t plus 120 degrees minus phi. So this is the expression. Close the bracket. So what will be this equal to? We have to further simplify this, and this whole thing you have to divide by root 3. Whole divided by root 3. I don't have space here, so you have to divide it by root 3. So this is QT. Or I can write this instantaneous reactive power QT equal to. What I will do is that I have root 3 here. I have root 2 into root 2. Okay, root 2 into root 2 is 2. See, actually you have minus 1 by root 3 here. And if you take this root 3 from all the expressions out, so it is root 3. Okay, I am taking root 3 outside. I already have 1 by root 3, minus 1 by root 3, of course, multiplied by this root 3. Root 3 I am taking common. What I get from inside is this. What is root 2 into root 2? Root 2 into root 2 is 2. Then Vi. Let me write this term first. Sine omega t minus phi into sine omega t minus 90 degrees. Okay. Then plus root 2 into root 2 is again 2. Then this is V, this is I, Vi. Okay. Then I will write this term first. Sine of omega t minus 120 degrees minus phi into this sine of omega t plus 150 degrees. Then similarly in the third term, root 3 I have already taken out. Root 2 into root 2 is 2 Vi. So 2 Vi. Then I will write this term first. Sine of omega t plus 120 degrees minus phi into this term. Sine of omega t plus 30 degrees. Fine. So let us try to simplify it further. So instantaneous reactive power therefore will be equal to this root 3 and root 3 goes, right? I can take this Vi. In all the three equations there is Vi. I can take this Vi out. So I get minus Vi times. So what I get is 2 sine of omega t minus phi into sine of omega t minus 90 degrees. This is first term. This plus 2 Vi already I have taken common. It is sine of omega t minus 120 degrees minus phi into sine of omega t plus 150 degrees. Fine. Then plus 2 sine of omega t plus 120 degrees minus phi into sine of omega t plus 30 degrees. That's it. Now this is 2 sine A sine B. Similarly here 2 sine A sine B, 2 sine A sine B. Using this trigonometric identity, that is 2 sine A sine B. What is that equal to? That is equal to cos of A minus B minus cos of A plus B. We will use this trigonometric identity. Using this trigonometric identity, what we get? See what we will get. Qt, that is instantaneous reactive power, is equal to minus Vi. Now this is 2 sine A sine B, that is equal to cos A minus B minus cos A plus B. Cos A is omega t minus phi. Minus B is this. So minus omega t plus 90 degrees. Minus cos of A plus B minus cos A is omega t minus phi plus B is omega t minus 90 degrees. Fine, that is first term. Then plus, this is again 2 sine A sine B, that is cos of A minus B. Cos of A is this, omega t minus 120 degrees minus phi minus B is minus omega t minus 150 degrees. Minus cos of A plus B. A is omega t minus 120 degrees minus phi plus B is omega t plus 150 degrees. Okay, that is second term. Then third term, this plus 2 sine A sine B, this is A, this is B, that is cos of A minus B. Cos of A is omega t plus 120 degrees minus phi minus B is omega t minus 30 degrees. Minus cos of A plus B. A is again omega t plus 120 degrees minus phi, omega t plus 120 degrees minus phi plus B is omega t plus 30 degrees. That's it. Let us further simplify it. So this comes out to be minus Vi times cos of this omega t and omega t goes. It is 90 degrees minus phi minus cos of omega t plus omega t is 2 omega t. Okay, it is 2 omega t, then minus 90 degrees minus phi. Okay, Then plus here also omega t and omega t goes. This is cos of this is minus 150 minus 120, but that is minus 270 degrees, and cos of 270 degrees is 0, and cos of 90 degrees is also 0. So instead of writing 170 degrees, I can write 90 degrees minus 5. So I hope this is clear to you. See, 150 plus 120 is 270, and cos of 270 is a 0 crossing. Cos of 270 is 0. Cos of 270 is 1. Okay, see, 150 degrees plus 120 degrees, it's 270 degrees. It belongs to 0 crossing. And what is cos of 0? 1. And instead of writing 270 degrees, can't I write 90 degrees? Because 90 degrees is also this. This is 0, 180 degrees. I think, yeah, it is 180 plus 90 is, yeah, 270. It's not, I'm sorry, it is not 0 crossing, it is the peak. This is 0, 180 degrees, 270 degrees. Okay, so this is 150 degrees plus 120 degrees is 270 degrees. Is it 270 degrees same as 90 degrees? Because what is cos 90 degrees? That is 0. Cos 270 degrees is also 0. So therefore, symmetrically, instead of writing this 270 degrees, I can write 90 degrees. So that these become symmetrical. Minus 5. Minus cos of omega t plus omega t is 2 omega t. Minus, now this is 150 minus 120, 150 minus 120, that is 30 degrees. Minus 5. Then third term plus cos of, here also omega t and omega t goes. So it is 120 minus 30 is 90 degrees. Minus 5 minus cos of omega t plus omega t is 2 omega t. 120 plus 30 is 150 degrees. Minus 5. So now you will get some very interesting thing. Cos of 90 degrees minus 5 is sine phi. So this is sine phi, this is sine phi, this is also sine phi. So therefore I can write qt equal to minus vi. What is inside? Sine phi plus sine phi plus sine phi. 3 sine phi. Then minus these terms. Cos of, I can write them within the curly brackets, cos of 2 omega t minus 90 degrees minus 5. Then second term is this, minus cos of 2 omega t plus 30 degrees minus 5 minus cos of 2 omega t plus 150 degrees minus 5. So let me write them this way. I can write qt equal to minus vi times 3 sine phi minus, अगर मैं माइनस बाहर निकाल रहा हूँ तो ये सारी टर्म्स प्लस हो जाएगी, प्लस दिस विल आल्सो बिकम प्लस, bracket closed. Now let me first of all write this term. Okay, this is cos of 2 omega t plus 30 degrees minus 5. Okay, उसके बाद मैं ये टर्म लिखूंगा प्लस cos of 2 omega t plus 30 degrees minus 5 plus 120 degrees. Can't I split this 150 into 30 plus 120? Yes, I can do that. तो ये अलग और ये अलग. Okay, then plus I am left with this term, cos of 2 omega t plus 30 degrees minus 5 plus 30 degrees minus 5 plus 120 degrees. Sorry, rather minus 120 degrees. Minus 120 degrees. Okay, minus 120 plus 30 is minus 90. So minus 90 can be split into plus 30 minus 120. Why I am doing it? Because it brings symmetry. Now if you solve this, cos of 2 omega t plus 30 degrees minus 5 plus cos of 2 omega t plus 30 degrees minus 5 plus 120 degrees plus cos of 2 omega t plus 30 degrees minus 5 minus 120 degrees. The summation of these three terms will be equal to 0. So therefore what you are left with, qt is equal to minus vi times 3 sine phi plus 0. So that will give you instantaneous reactive power equal to minus 3 vi sine phi. That's it. So we got it only with the help of Akagi's equation that we used in the previous lecture using ABC to alpha beta O transformation. Actually we had got instantaneous reactive power equation like this, minus 1 by root 3 VBC IA plus VCA IB plus VAB IC. We require these line voltages expressions using phasor algebra, phasor diagrams. We got the mathematical expressions for line voltages VAB, VBC and VCA. And then we already know the expressions for line currents IA, IB, IC. We substituted them and we ended up with this mathematical expression. So therefore instantaneous reactive power finally after the substitution is minus 3 VI sine phi. So therefore the above values of above value of instantaneous reactive power we have got from the expression which was derived in the previous lecture using Akagi's coordinate transformation. So therefore what we have learned in today's lecture, we have whatever we had discussed in the previous lecture, we use that knowledge. Okay, in the previous lecture we got the expression for instantaneous power as Vi 3 Vi cos phi. Today also we got the same expression, but in previous lecture we were not having the instantaneous the equation for instantaneous reactive power. For getting instantaneous reactive power we had to use the coordinate transformation, and then from that coordinate transformation we got this expression for instantaneous reactive power, which you already know, which I have written a few moments back. So what we did, we substituted the line voltages VAB, VBC, VCA and line currents IA, IB, IC in that equation, and we got the final expression for reactive power as 3 VI sine phi. So we got the expression for instantaneous active power or instantaneous power and instantaneous reactive power using phasor algebra. What we did, we drew the phasor diagram, and from the phasor diagram we got the expressions for line voltages VAB, VBC and VCA, substituted those into this equation, we got the expression for instantaneous reactive power. So therefore active instantaneous power expression is PT equal to 3 VI cos phi, which is a constant term, and instantaneous reactive power from this expression comes out to be 3 VI sine phi. I will stop here. The same logic we will use, the same method, the same approach we will use inshallah in next lecture. In the next lecture we will consider three-phase unbalanced system without harmonics. This was a three-phase balanced system, and in the next lecture we will consider three-phase unbalanced system, and using the same approach we will try to derive the mathematical expression for instantaneous power, instantaneous active power, instantaneous reactive power, and see how that is different from that of a three-phase balanced system. So I wish you all the best. I advise all of you to go through this lecture, try to derive these expressions yourself, draw the phasor diagram, and from the phasor diagram try to get line voltages, substitute those line voltages into that Akagi's equation and get the expression for instantaneous reactive power. In case of any doubts, any difficulties, please feel free to ask me. Thank you.